Hello everyone, welcome to another episode of Math-321, and today we're going to conclude Investigation 25 on the symmetric groups. So let's get started. Okay, so first let's define what a transposition is. So a transposition is a two-cycle, or a cycle that just swaps two elements. So all cycles can actually be expressed as products of transpositions, and there's multiple ways to do it. So the first way here is probably the easiest to remember. If you have a cycle from A1 up through AK, you can just break that down into A1, A2, A2, A3, A3, A4, dot, 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 up through AK minus 2, AK minus 1, and AK minus 1, AK. So everything pretty much stays in the same order. Keep in mind, of course, when you want to actually figure out what the right-hand side is or how it works, you're applying the rightmost transposition between AK minus 1 and AK first, and then you do the second to most right one, and so on and so forth up through the left one. So there's a lot of different ways to do this. Like I said, this is another way that you can express the same cycle, and there could be lots of different ways to do it. So since every permutation can be expressed as the product of cycles, that means that every permutation can also be expressed as the product of transpositions. However, unlike with cycles, the transpositions are not guaranteed to be disjoint from each other. As you can see, these ones here that I have listed are not disjoint from each other. Okay, so let's try an activity. So I want you to, I forgot to put the directions on here, I think, but I want you to express these three permutations here as products of transpositions. So go ahead and give that a try, pause the video, and then we will go over it. Okay, so let's go over the answers here. So I think what I'm going to do is I'm first going to write these as products of cycles, and then I'm going to transform each cycle into a product of transpositions. I think that'll be the easiest. So let me do it as cycles first. So I'm just going to start with 1, and then 1 goes to 2, and then 2 goes to 4, and then 4 goes back to 1. So that's the first cycle. And then I'll start with 3. Actually, 3 just goes to itself, so I'll skip that one. Let's see, what's next? 5. Okay, 5 goes to 7, and then 7 goes back to 5. So that is a transposition. And then what did we skip? So we skipped 3 and 6, but those both go to themselves, so we can leave them out. Okay, so the only cycle I need to break down here is 1, 2, 4, and I can write that as 1, 2, 2, 4. And then 5, 7 can stay as it is. Okay, so you can check that if you want and just make sure that everything really gets mapped to the right place. Like for example, the element 4, so 4 doesn't go anywhere from this transposition, so then the next transposition would be this one, and that one maps 4 to 2, and then we go to the last one, and then that one would map 2 to 1, so in all 4 does get mapped to 1, just like it is supposed to. And you can check that for all of them if you want to. Okay, let's do the next one. So I'm going to start with 1. So 1 goes to 1, so I'll skip that. 2 goes to 2, so I'll skip that. Okay, 3 goes to 5, and then 5 goes to 4, and then 4 goes back to 3. So that's that cycle. Okay, and then let's try 6. That goes to itself. So 7 goes to 8, and then 8 goes back to 7. So that's that cycle. And I think that covered everything that's not mapped to itself. So I can just break down this first cycle into 3, 5, 5, 4, and then we have 7, 8. Okay, let's try the last one. So I'm going to start with 1, which is mapped to 6, and then 6 goes back to 1. Okay, let's move on to 2. 2 goes to 10, 10 goes to 3, 3 goes to 9, 9 goes back to 2. Okay, let's see, what did we skip? 4, that goes to itself, so 5 goes to 7, and 7 goes back to 5. Okay, let's see, 8 goes to itself, and so I think we covered everything that's not mapped to itself. So I just need to break down this middle cycle into transpositions. So I'll do 2, 10, 10, 3, and then 3, 9. And that's it. Okay, so now let's talk about an interesting property of transpositions. So theorem 25.14, let n be a positive integer and let sigma be an element of the symmetric group on n elements. No matter how sigma is written as a product of transpositions, the number of transpositions in the product will always have the same parity, in other words, the same evenness or oddness. So this is interesting, and it actually allows us to characterize every permutation as either even or odd according to how many transpositions it can be written with. So the next two lemmas are going to help us prove this theorem 25.14. Okay, so here is the lemma, and this is actually 25.14 and a half, which means it's something that I inserted that was not in the textbook. When I read the proof of the next lemma in the textbook, I thought it was kind of confusing and left out some details, so I wanted to put this extra little helping lemma in here to help us prove the next lemma. And so both of these lemmas are going to support the proof of the theorem, which will be quite easy once we have these two lemmas. Okay, so here it is, lemma 25.14 and a half. So let n be a positive integer and let sigma 1 and sigma 2 in the symmetric group on n elements be transpositions. And let I be the identity in Sn and let A be an element in the set 1 through n, which is permuted by sigma 2. And note here that what I mean by A being permuted by sigma 2, that means that sigma 2 maps A to an element that is not A. So sigma 2 is not the identity on A. Okay, does that make sense? Okay, then the result of the lemma is we have one of two things. So either sigma 1 times sigma 2 is the identity, or there exist transpositions rho 1 and rho 2 in Sn, such that sigma 1, sigma 2 equals rho 1, rho 2, and A is permuted by P1 and by rho 1 and not by rho 2. Okay, so this is a little bit complicated and technical, but this would be really, really helpful in proving the next theorem. Okay, so basically if you have a product of two transpositions and A is one of the elements that is in the second transposition, then there's a way to write those two transpositions as two different transpositions where A is not moved by the second transposition, but it is moved by the first transposition. So like I said, it's a little bit technical and might seem kind of useless, but it'll actually be really useful in the next lemma's proof. So let's go ahead and prove this. All right, here's the proof, and it's all just on this one slide here. I just put the lemma up in the corner so you can look at it while you're reading the proof. So let n be a positive integer, and let sigma 1 and sigma 2 in Sn be transpositions, and let I be the identity in Sn, and let A in the set 1, 2, ... n be an element that is permuted by sigma 2. So that's all just copied and pasted from the lemma statement. Okay, so here's the new parts of the proof. So let sigma 2 be the permutation of A and B. We already knew it permuted A, so we had to put that one in there, and then we just have to put something else, so I'm calling it B. Then there are 4 possibilities for what the elements in sigma 1 can be. Okay, so here are the 4 possibilities. Number 1, sigma 1 and sigma 2 have both elements in common. That is, they're actually the same transposition. So if you multiply a transposition by itself, or in other words, you compose it with itself, then what you're doing is you're swapping the elements and then you're swapping them back. So that is just the identity. Okay, so that leads to case 1 of the lemma statement. That's that first one there where it says sigma 1, sigma 2 equals I. Okay, so that's that. All right, and then the other 3 cases are going to give us that second case, this one, in the lemma statement. So these 3 here are going to give us this one. Okay, so the other 3 possibilities, so the second and third ones are where sigma 1 and sigma 2 have one element in common, and then that one element could either be A or it could be B. Okay, so in case 2 here, sigma 1 and sigma 2 have one element in common, A, and so we're just going to call the other element of sigma 1 by the name C. So then sigma 1, sigma 2 equals AC times AB, and you can actually rewrite that as ABC, and you can rewrite that as ABCB. So you guys can check all that if you want to, but that's pretty easy to check. So let's look at the third case here. Sigma 1 and sigma 2 have the other element in common, b. So we're just going to, again, call the other element of sigma 1 that is not b, we're going to call that c. Then we can write sigma 1 times sigma 2 like this, cb, ab, and we can rewrite that as acb, and we can rewrite that as ACCB. And again, that's stuff you can check if you want to. Okay, and then case 4, sigma 1 and sigma 2 have no elements in common. So we're going to call the elements of sigma 1 C and D, so neither of them is A. And then sigma 1 times sigma 2 equals CD times AB, and since CD and AB are disjoint from each other, we can actually just swap those around in the other order and write them as AB times CD. Okay, so what you see here is that in case 1, we had that sigma 1 times sigma 2 equals I, and then in the other 3 cases, we have actually found 2 transpositions, row 1 and row 2, such that sigma 1, sigma 2 equals row 1, row 2, and A is permuted by row 1 and not by row 2. Okay, so if you look at these here, this is row 1, this is row 2, and you see that A is in row 1, but it's not in row 2. And that's the same for all of these. A is in here, but not in here. A is in here, but not in here. And again, this probably seems pretty meaningless until you see how useful it actually is in the proof of the next lemma. So let's go ahead and look at the next lemma. Okay, so lemma 25.15, this is the one that was in the book. So let n be a positive integer, and let I be the identity permutation in Sn. If I equals tau 1, tau 2, tau k, where tau 1, tau 2, tau k are transpositions, then k is even. So this is saying that if you're able to write the identity element as a product of transpositions, then it must be an even number of transpositions. So this is interesting. Why would that be the case? Kind of mysterious. But let's go ahead and have a try at proving it. And I will warn you that this proof is pretty challenging and technical. There's like a million subscripts, which are enough to make your head swim. And there's many cases. So yeah, just take it slowly, and if you need to like back up and listen to certain parts again, or if you need to like read the version that's in the book or anything, that's totally fine. I think it took me about an hour to work through understanding this proof myself. But it's good for your brain to practice understanding proofs. So let's give this a try. Okay, so we start by letting n be a positive integer and let I be the identity permutation in Sn. Then we're going to proceed by strong induction. So here's the statement that we're going to use for the induction. So let P of k be the statement, if I is the product of k transpositions, then k is even. So that's what we're going to try to prove, and we're going to try to prove that that is true for all values of k greater than or equal to 2. So just note here that we don't actually need to prove this for k equals 1 because it's impossible for the identity to equal 1 transposition. One transposition always moves or permutes 2 elements, so that wouldn't be the identity. Okay? So for the basis step, suppose that I is the product of k transpositions, where k equals 2. So basically we're trying to prove P2. Well, just by the supposition that we've made that I is the product of 2 transpositions, then k is even because 2 is even. So that's this part right here is like the easiest basis step that you'll ever see. Okay, so let's try the inductive step. So for the inductive step, let's assume that P2, P3, all the way up through Pk are all true. Then what we want to show is that P of k plus 1 is true. So in other words, we want to show that if I is the product of k plus 1 transpositions, then k plus 1 is even. So let's give that a try. Okay, so we suppose that I is the product of k plus 1 transpositions, and we're calling the k plus 1 transpositions this, so we're calling them all tau. I guess tau is the Greek letter T, so that actually stands for transposition. So we're going to try to show that k plus 1 must be even. Okay, so here's where we're going to start. We're going to start at the end. So let one of the 2 elements that is permuted by by tau k plus 1 be called A. Then we're going to apply lemma 25.14 and a half. And we have two cases. So basically we're looking at these last two transpositions here together, and we're applying lemma 25.14 and a half to those two transpositions, okay? And because A is permuted by the second one of them, we can easily apply that lemma 25.14 and a half. So that gives us two cases because there were two possible outcomes from lemma 25.14 and a half, and they are these. So the first possible outcome is this, that tau k times tau k plus 1 could equal the identity. So if that's the case, then that's actually great because we can just cancel those two off of the end of that product, and then we would get that I equals tau 1, tau 2, dot, 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 up through tau k minus 1, which would be a product of k minus 1 transpositions. And then since we assumed that P of k minus 1 is true, in other words, that whenever I can be written as the product of k minus 1 transpositions, that would mean that k minus 1 is even. So then if k minus 1 is even, then k plus 1 would be even as well, and we would be done. So we would have proven P of k plus 1. So that's one case, and that's the one you sort of hope you get. But then the trickier case is, all right, the other outcome that was possible from lemma 25.14 was that we would get those two other transpositions, rho 1 and rho 2, that would equal sigma 1 times sigma 2. So, but in this case, we're not using sigmas and rhos, we're using taus, and we're also using alphas. So the way I'm going to state that result is the following. There exist transpositions alpha 1 and tau k prime in Sn, such that tau k times tau k plus 1 equals alpha 1 times tau k prime, and A is permuted by alpha 1 and not by tau k prime. So that's all exactly the same as in lemma 25.14, except instead of sigma 1, sigma 2, I'm using tau k plus 1, and instead of rho 1 and rho 2, I'm using alpha 1 and tau k prime. Okay, so I've just given them different names, and it might become clear why they're being named like this. It's just a little more systematic of a way to name them. Okay. So if we do get case 2, then continuing on with that, what we can do is we can substitute that back into our product of transpositions of I to get this product here, tau 1, tau 2, dot, 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 tau k minus 1. And then instead of tau k and tau k plus 1, we have alpha 1 and tau k prime. Okay. And then, this is where it starts to get weird, is since alpha 1 permutes A, we can apply lemma 25.14 and a half again to this product right here, tau k minus 1 times alpha 1. So we can apply lemma 25.14 and a half again using tau k minus 1 alpha 1 instead of sigma 1 sigma 2 from that lemma 25.14 and a half. Okay? And so because we're applying that lemma again, we get two more cases. So let's look at those two cases. Okay, so here are the two cases. So this is all just from the last slide again. So we're applying that lemma again, and here are our two cases. So the first case is that tau k minus 1 times alpha 1 might equal the identity. So if that is true, if it does equal the identity, then here I've just written again what we currently have I equaling. And then on the next step, we would be able to replace this part right here with I. Okay, so that would just cancel out and it would just leave you with this, which is a product of k minus 1 transpositions. So since we assumed P of k minus 1 is true, that would mean that k minus 1 is even, and so that would mean that k plus 1 is even as well, and then we would be done. So that would be great if that happens. But if that doesn't happen, then we get the other result from lemma 25.14 and a half, and the other result would be the following, that there would exist two more transpositions, which this time, instead of rho 1 and rho 2, I'm going to call them alpha 2 and tau k minus 1 prime. Okay, there would exist those other two transpositions such that the transpositions we started with, which are here, tau k minus 1 alpha 1, would equal alpha 2 tau k minus 1 prime, and they would have the property that A is permuted by alpha 2 and not by tau k minus 1 prime. So A is permuted by the first one here and not by the second one. Okay, so if that is the case, so continuing on with case 2b, then we can continue to rewrite I in the following manner. So we could rewrite it like this. Okay, so what I've done there is I've just replaced this part, tau k minus 1 alpha 1. I've replaced it with this part right here, alpha 2 tau k minus 1 prime. Okay, and then I just pulled out this part, the tau k minus 2. I pulled that out from the dot dot dot. Okay, so that's not appearing out of nowhere. That was in the dot 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 up here. Okay, so, well, now it gets a little weird again because you see that alpha 2 permutes A. So we could apply lemma 25.14 again to this part of that product. Let me just circle it to this part. Okay, so we have again another product of two transpositions where the second one of them permutes A. So that's the condition in which you can apply lemma 25.14. And then that would give us two more cases. And at this point you're like, oh my god, stop bringing out cases. And I'm like, yes, I do want to stop. No more cases, please. This is too many cases. So at this point we're going to dispense with the case insanity. And I'm going to sum up what happens with the cases on the next slide. Okay, so basically we can continue in this fashion. We can just keep applying lemma 25.14 again and again and again and again and breaking into more and more and more subcases. But there are really only two ultimate possibilities. So basically we either never get case 1 from lemma 25.14 and remember that case 1 was where your product of transpositions was the identity, or at some point we do get that case 1. So you either never get it or at some point you do get it. So let's look at what happens in those two possibilities. So suppose that we never get case 1 of lemma 25.14. Then what I'm going to do is I'm just going to continue on with this like very complicated process of just repeatedly pulling out two transpositions that are next to each other from the identity and just replacing them with two different transpositions that I get from lemma 25.14. And if I just continue the pattern that I've been making with all the subscripts and the taus and the alphas and stuff, then eventually if I never get case 1, then I'll eventually end up with this. So I'll end up replacing all of the taus with tau primes, and that alpha term will just keep getting moved further and further left until it's the furthest left transposition. Okay, and I'm going to also end up with the following property, that A is permuted by alpha k. So that was true in the two cases that we saw before. A was permuted by alpha k and not permuted by any of the tau primes. Sorry, there was a little jump there. I'm having some recording difficulties. Okay, so if we do end up getting I into that particular form, then the problem is that's a contradiction, because if A is not moved by any, if it's not moved or permuted by any of these permutations here, and it's only permuted by this one, then that means that A ends up getting permuted by that entire product as a whole. But that's not possible because that entire product as a whole is supposed to be the identity. So A is not supposed to be moved by the identity. Okay, so that means that that doesn't happen. We are never able to completely get to that end state of this product right here. It doesn't happen. So that means that at some point we must get case 1 of lemma 25.14. So as we continue that process of just applying that lemma over and over and over and breaking into subcases, at some point we get that first case 1 result from lemma 25.14. And so in other words, there's some I such that we get the following. The identity equals this. So this is quite complicated. It's a lot of subscripts floating around in there, but that is what the pattern would look like if you just continued doing a replacement using that lemma and just kind of stopped in the middle somewhere at an unknown point called I. That's what the subscripts would look like. And then if you do get that case 1 result, then you would be able to replace this part, tau k minus 1 alpha I, which is right here. You would be able to replace that with the identity. Okay, so if you're able to replace that with the identity, then you get this result right here, which is also kind of complicated. But basically, I hope what you can see is that if you count up how many transpositions are in that part there, you've got k minus 1 of them, because the subscripts start at 1, and then they go to 2, and then they end at k. And then right in the middle here, between these two subscripts, you skip over one subscript. So that means there would be k minus 1 of them. Okay, so that would be a product of k minus 1 transpositions. And then since we assume that p of k minus 1 is true, that means that since we express the identity as the product of k minus 1 transpositions, that means k minus 1 must be even, and that implies that k plus 1 is even as well. So that implies that k plus 1 is true, and so that ends the proof. The lemma result follows by mathematical induction. Okay, so that was quite complicated. I hope you hung in there. Like I said, it took me about an hour to understand this proof myself, so I will not be surprised if your heads are swimming in subscripts right now. Okay, so let's move on to the proof of the actual theorem. Okay, so let's go ahead and prove theorem 25.14. And first let's just read it again. So let n be a positive integer and let sigma be in Sn. No matter how sigma is written as a product of transpositions, the number of transpositions in the product will always have the same parity, in other words, the same evenness or oddness. Okay, so here's the proof. Let n be a positive integer and let sigma be in Sn. Assume that tau1, tau2, tau k, and alpha1, alpha2, alpha m are transpositions such that sigma equals the product of all the taus and sigma equals the product of all the alphas. So in other words, we've expressed sigma as a product of transpositions in two different ways, and now what we're going to show is that the number of transpositions in each expression have the same parity. So we're going to show that k and m have the same parity, which is equivalent to showing that k plus m is even. So you might need to take a minute to stop and think about why that is equivalent to showing that k plus m is even. So if k and m are both odd, then an odd plus an odd is even, and if k and m are both even, then an even plus an even is also even. However, if one of them is even and one of them is odd, then you have an even plus an odd, which would be odd. Okay, so we just need to show that k plus m is even. And so what we're going to do is pretty easy. So we take this equation here where we've got the two expressions for sigma equated to each other, and then we're going to multiply by alpha m minus 1, through alpha 1 on the right. And so what this is going to do is going to work because every transposition is its own inverse. Remember, if you swap two numbers and then you swap them again, then you've swapped them back. Okay, so you basically did nothing if you swap and swap back. Okay, so what's going to happen here is we're going to get tau1 through tau k times alpha m through alpha 1 on the left side, and then on the right side we have alpha 1 through alpha m, and then alpha m back down through alpha 1. And so these are going to cancel out. The alpha m and the alpha m are going to cancel each other out, and then alpha m minus 1 is going to cancel out with something else inside the dots here, and you're going to keep canceling back and forth until you get down to the last pair, and then they'll cancel each other out. Okay, so that whole right hand side is going to cancel from the center to the outsides, and then you're going to have left just that tau1 through tau k times alpha m through alpha 1 is equal to the identity. And so now is where we get to apply lemma 25.15. All that work we did proving that was so that we could use it right here. Since we have written the identity as the product of k plus m transpositions, by lemma 25.15, k plus m must be even, and so k and m have the same parity. And that's it. So sometimes in math, you work really, really, really hard on a lemma and then you just use it in one little spot, but that's what they're for. Okay, so this next concept here, this is a consequence of that theorem that we just proved. So definition 25.16, let n be a positive integer. A permutation sigma in Sn is even if sigma can be written as a product of an even number of transpositions. And a permutation sigma in Sn is odd if it is not even. So in other words, if it can be written as an odd number of transpositions, then it's odd. So we can characterize every permutation as either even or odd, which is interesting. So let's try something with that. Let's try doing this activity right here. So just a hint for you, these are actually the same permutations as in activity 25.13. So go ahead and try these, and then we will go over the answers. Okay, so let's go over these answers. So in case you forgot what they were from before, I'm just going to write down what these were as transpositions again. So this was 1, 2, 2, 4, 5, 7. This one was 3, 5, 5, 4, 7, 8. And this one was 1, 6, 2, 10, 10, 3, 3, 9, and 5, 7. So these are all actually odd. Okay, and that's it. Okay, so let's talk about the next concept. So an interesting question is the following. Does the set of all even or odd permutations, does it form a subgroup of Sn? So here's an activity to help you think about that. So go ahead and pause the video, give this a try, and then we will talk about it. Okay, so let's go over these answers. So part A, explain why the collection of odd permutations is not a subgroup of Sn. Hint, is the product of two odd permutations an odd permutation? Okay, so the answer here is that the product of two odd permutations is actually an even permutation. So it's like super not closed under the group operation. So just to give you a little example, let's say alpha equals 1, 2, beta equals, I don't know, 3, 4, then alpha and beta are odd, but alpha times beta, which is 1, 2, 3, 4, is even. Okay, so if you multiply an odd permutation times an odd permutation, then the number of total transpositions there will be an odd plus an odd, which would be even. Now, on the other hand, is the product of two even permutations always an even permutation? This is going to be true. So yes, if, let's say, alpha and beta are even permutations, then say alpha is the product of 2n transpositions, and beta is the product, why did my p disappear, is the product of, let's say, 2m transpositions, so those are even numbers. So for some n and m in the integers, then alpha beta is the product of 2n plus 2m equals 2n plus m transpositions, which is an even number. Okay, so the collection of even permutations is in fact closed under multiplication or composition, however you want to think of that operation. Okay, let's look at part C. So is the inverse of an even permutation always an even permutation? So the answer here is yes, and I'll show you why. So yes, suppose sigma equals, let's just call it again, tau 1, tau 2, dot dot dot, through tau n, where n is even. Okay, then sigma inverse, the way you write the inverse when you have it in terms of transpositions is you just reverse them all. So it's tau n minus 1, dot dot dot, up through tau 2, tau 1. So I hope you can see that if you would multiply sigma times sigma inverse there in either order, that you'll get cancellation starting from the middle and then moving towards the outsides, because every transposition is going to cancel itself. But let me just show you that if it's not making sense. So then sigma 1, for example, equals t1, t2, or sorry, tau 1, tau 2, tau n, tau n minus 1, dot dot dot, tau 1 at the end. So what's going to happen is you'll get this kind of like collapsing cancellation, where this is, so these two are going to cancel, and then you'll have this up through tau n minus 1, and then tau n minus 1, and through tau 2, tau 1, and then those two are going to cancel, and then it'll just keep collapsing on itself like that until you get down to, like, let's just say you keep going like that, you'll have, you know, tau 1, tau 2, and then tau 2, tau 1, and then those will cancel, and then you'll have tau 1, and that'll cancel, and you'll just have the identity. Okay, and then it's the same in the other order. It just goes the same way. Right, so I think what you can see there is that sigma and sigma inverse, they have the same number of transpositions in them because you just reverse the order. Okay, so let's talk about part D here. So let AN be the set of all even permutations in Sn. Explain why AN is a subgroup of Sn. Okay, so we pretty much verified the 4 things that you need. So we need that it's closed under the operation, which we're thinking of it as either multiplication, but that's really just a shorthand for function composition. So it's closed under that. We talked about that. Contains the inverses of all elements. We did that. Inverses. What else do we need? We need that the operation is associative. We didn't talk about that, but why is that the case? This is actually just inherited from wait a minute, how do I spell inherit? Inherited from Sn. So all the elements in An are also elements of Sn. So they'll be associative because Sn is associative. Okay, and then lastly, what's the last thing we need? Closed, inverses, associative. I know there's a 4th one. Ah, yes, the identity. So we need that AN contains the identity, and we have this from that long lemma that we proved. So I is going to be even because of the lemma. I don't remember what number it was anymore. 25.14 maybe? Oh well. Okay, so this brings us to the definition of the alternating group. So for n greater than or equal to 2, the alternating group AN is the subgroup of Sn consisting of the even permutations of Sn. So it's that group that we just showed was a group in the last activity. So activity 25.20, find all of the elements of A3. So go ahead and pause the video and do that, and then we will go over it. Okay, so let's go over this activity. So I think what I'm first going to do is just list all of the elements of S3 in transposition form, and then I'll just figure out which ones of them are even. Okay, so S3 has the following 6 elements in it. So I think it's easiest for me if I just put them in the regular permutation form, because then I can make sure that I covered all 6 possible orders that 3 numbers can be rearranged into. Okay, so this is going to be 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and then I'll put them into cycle form, and then I'll put them into transposition form. So I don't know how you guys did it, but I think this is the most systematic way for me to try to do this, and I'm just listing them now in numerical order. 2, 3, 2, 1. Okay, so now let's put them into cycles. So obviously this is just the identity, so I don't really need to worry about this one. This one is a transposition. It's just the transposition of 2 and 3, so that one's easy. This one, okay, let's see. So this is the transposition of 1 and 2, so that's easy as well. This one, I believe, is a 3 cycle, so let's see. 1 goes to 2, and then 2 goes to 3, and 3 goes back to 1. So I can write that in transpositions as 1, 2, 2, 3. Okay, and then this one is going to be, let's see, it's another 3 cycle, I think. So 1 goes to 3, and 3 goes to 2, and 2 goes back to 1. So in transpositions, that'll be 1, 3, 3, 2. And then finally, the last one is just the transposition of 1 and 3. Okay, so which of these are even transpositions? So that's going to be I, because it's 0 transpositions. So I is in the alternating group, and then also 1, 2, 2, 3 is in the alternating group, and finally 1, 3, 3, 2 is in the alternating group, and it's just those 3 elements. So there's an interesting fact that the alternating group, which is the even permutations, always contains exactly half of the elements in Sn. Just like how in the integers, half of them are even and half of them are odd. It's kind of interesting. You wouldn't necessarily expect that that would be the case. There's a couple paragraphs in the book that are about that, but I left it out of the lesson for today. So that's everything for today. Hope you watched up until the end. Like I said, if you're still confused about those proofs we did, that's totally fine. I would suggest try to study them and work them out and make sense of them. That's good for your brain, especially those of you who are going to continue on to graduate school. You're going to encounter a lot of proofs like that, and maybe even called upon to write some. So thanks for watching today, guys, and I will see you next time.